Is an attempt to actually try to shed some light on what deep networks are actually doing, and we'll see how far we can actually get with that. So this slide that I showed you yesterday, again, it's, to me, for me, it's better to think of deep networks as functions that compute image representations. That's a very useful view. And so remember, an image representation is just a function that maps an image x to some vector, phi of x, which somehow help us extract the information we want. And of course, you know, we have been talking about deep convolutional neural networks for the past 2 days, so you're already familiar with this, hopefully. That's an example of possibly the most famous network for computer vision, AlexNet. And already we said that this is really good because it gives you excellent performance, gives you transfer learning, and many other things. That's cool. But of course, there is a downside to this, and the fact that the fact is that the model is a black box. This contains a couple of millions of parameters. They are learned from millions of images. Really, we don't know what's happening in there. Okay? So the goal of this session is actually to try to shed some light on the meaning of, well, essentially what these neurons actually have learned, and when you process an image, what they actually do to the image. Okay? So this is in 3 parts, and I'm going to start by discussing visualizing representations. And so this is the starting point. This is going to be, at the same time, a little bit abstract, as well as intuitive. I hope it's going to be interesting. So here we have 2 spaces. We have the image space that for now is empty, and then we have a representation space. Okay, so this is where the output of your neural network actually lives. So this is just a high-dimensional vector. Okay. In fact, this doesn't even need to be phi of x. Doesn't even need to be a neural network. It could be any image representation. In fact, in this particular instance, what I'm showing here are the slices computed by, not by a CNN, by another feature which is called HOG, which was very popular before CNNs in computer vision. By the way, HOG is also a special case of a CNN, if you like, but it's not learned, it's untracked. All right, so I have my image representation, phi of x, and now what I want to know is what information is contained in that vector. So one thing I could do is to try to take phi of x and get back my image. Okay? So this is a sort of inverse problem, if you like, because what we have is the function phi that goes from the image to the representation. That's your neural network. But what we want to do here is to go from the representation back to the image. Okay? Now, these networks are actually designed not to be injective functions. So if I say injective functions, do you know what it means? Yes? Okay. So that means that there's going to be, in general, a second image here that happens to map to the same point in the representation space. So why is that? Well, if you think about it, if you go deep down enough, a neural network like AlexNet, at the very last level, phi of x will be a list of possible image labels, right? So that vector, in theory, only depends on the content of the image. So in this case, it's going to tell you that there is a dog in there. It will not depend on a specific characteristic of the image. So it should not be able to, so all the dog images you have should map to the same vector in theory, all right? So this shows that this mapping is not injective. It means that when you try to do this inversion process in general, there are at least 2, in fact, in general, many more images that happen to map to the same point phi of x. So now what you want to do is to try to characterize the space of images, or an equivalence class of images, which happens to share the same representation by means of the network that I have learned. So in this way, I know that the network is essentially invariant to changes in the images which are intuitively captured by how these images in this set actually change. So here for HOG, you see that the color image up there is actually the same as the sort of contrast normalized and black and white image. That's because HOG throws away contrast, absolute level of intensities. It just remembers the gradients of the image, and also it throws away color information. So here you know from the fact that these 2 images map to the same HOG feature that these changes in the image space are actually irrelevant for the viewpoint of the network. So how am I going to do this in practice with a neural network that is not HOG, so just a general representation? Well, I'm going to pose this as a optimization problem. So I'm going to start with phi naught, which is the representation that they computed from a reference image, in this case this dog. And here you see the slices that you have from the output of some convolutional layer in your network. So this is phi naught. This is just a vector. I'm going to freeze that. And then I'm going to try to find another image x such that when I apply the same function to the representation to x, phi, I get phi naught back. And so to do that, I pose that as an optimization problem, and I try to minimize the distance between these two vectors, these two representations. So if I do that, what I get is a pre-image of phi of x, which in general won't be the same image we started with, but crucially, the representation of these two would be about the same. So it means that from the viewpoint of the network, these two guys are equivalent, okay? So it's very important here, and I'm going to stress this over and over again, that when you do this process, all you know about the image you want to reconstruct is phi naught, okay? So the inversion process starts from random noise. So initially, x is just a random matrix. And then the image you get out only depends on this optimization process that you solve by using gradient descent, okay? So there's no other information except a very mild prior on the low-level image statistics. So if you try to solve this problem here, and you start from a deep layer in the network, you get a result which maybe contains the dog a little bit here, but it's very hard to interpret. So what we're going to do is to add to this process of inversion two regularizers. In fact, just one regularizers in practice, because the other one is trivial. And this one just tells you that you want your reconstruction to have finite values. And that's needed because some of these networks have some normalization in them. So if you multiply this by 100, the representation wouldn't change. The other one is a little bit more informative, but just a little. So this is a TV norm of the image with some exponents. So in this case, beta is equal to 1, or beta equal to 2. Doesn't really matter what it means. But essentially, what this TV norm terms does is guarantees that the solution to this optimization problem is a little bit smooth. It means that the derivatives of this guy, on average, are not too big. All right? So let's see whether we have understood this at all. So why do you think if I take a network like AlexNet, I cut it at some deep level, for example, conv5, and I run my inversion process like this, and suppose I do not have these regularization terms, why do you think I get something like that as opposed to something like that back? Any idea? Okay, it's not obvious, but so remember, these networks, they are trained discriminatively, right? So the goal of the network is to be able to tell a dog apart from a cat, et cetera, et cetera. So deep down the network, you're going to get invariances. Most importantly, the network doesn't have any reason to remember information about the image, which is not useful for your discrimination task, right? Now, this kind of prior, the fact that the statistic of the gradient of a natural image are not random, but they tend to follow specific statistical laws, well, then every natural image will have that. So it's not useful information to be able to discriminate between a cat and a dog, because images of cats and dogs will have a smooth gradient. So a network which is trained discriminatively will throw away that information. So if you try to invert a network which has been trained like that, without restoring that information by means of a regularizer, then you get a result which is not very interpretable. All right? So the reason, again, is that the smooth gradient is not very useful discriminate information because all natural images actually have that anyway. So the network doesn't need to learn it. Now, there are a bunch of related visualization technology methods. So I will discuss some of these later, so I don't want to go into much detail, but here's a nice list of papers if you're interested in reading more about this. Now, let's use this tool to try to get some sense of what AlexNet actually does, all right? So this is a schematic representation of AlexNet. You have 5 convolutional blocks, and each one of them contains, well, filter bank, convolution, ReLU, max pooling, and LRN, which is this normalization which is not used anymore. Conv2, Conv3, Conv4, Conv5, and then you have the fully connected layers, which are also linear operators followed by a ReLU, all right? Now, this is an input image of a monkey, of course. So so this is the original image, and this is the reconstruction we get from the features we compute at this level in the network. Okay, so do these two look similar? Yes. So how much information is being thrown away by the network at this level? Not very much at all right? So as you might expect, the first level of filtering is essentially a bijective mapping between the image and the representation space that you get by cutting the network at this level. I should also say and remark that when you have a neural network like this, you get a different image representation at every single depth, right? So you can take the network, you cut it here, you're going to get a vector, which is a representation of the image, and you try to understand that. So now what we're going to do is to try to see, as we go deeper in the network, how the reconstructed image change, and that hopefully is going to give us some idea of the kind of information which is preserved by the network and what instead is thrown away. All right? So this is Con1. This is ReLU 1, I believe. Then max pooling. And this is local contrast normalization. Then you go on, Com2. And as you go on and on, you see that the reconstruction starts to become faster and faster. All right? So that means that the network somehow is forgetting about those details of the monkey, but it's still able to recognize the monkey because, very importantly, when I feed this image back to the network, the representation you get here is the same as you got before, right? So whatever happens after that is going to be the same calculations, essentially, that you got from the original image, which means that if this image was classified as a monkey, then this image here, because it's equivalent from the viewpoint of the representation at this level, also has to be classified as a monkey, right? So these two are equally good monkeys from the viewpoint of the network. Now you go on, you get further down, and at some point you see that, well, now the monkey has 3 eyes, okay? So the network is not really good at remembering the specific layout of the object. It only needs to know about a trace of the layout and still good enough for it. And as you go deeper, this starts to be very scrambled. And now these are still convolutional layers. It means that they tend to remember the kind of layout you got in the original image. But if you go deeper down, now this is the inversion from the fully connected laser here, you see that now the reconstruction is a lot more scrambled. Still, and despite the fact that the projector has pretty poor contrast, you can still sort of see the fur of the monkey, the nose, I guess, and the 2 eyes. Go deeper down, though, this becomes more and more scrambled, okay? Now you have an eye here, an eye there, you know, fur everywhere. Still, this is just as good as a monkey as that from the viewpoint of the network. So this is actually also quite interesting because it shows that maybe your network is even too much invariant, okay? Further down, and this is what you get at the very last level. So here we're inverting the last output of the network, which are these fully connected features which are supposed to classify your image as a monkey. So in theory, all you know at this level, at this point, is that the image contains a monkey. You shouldn't know anything specific about the actual monkey you have seen, all right? And here is a slide that summarizes everything I have said from Con1 to fully connected layer 8. So you can see the progression and how much information is being thrown away by the network as you go further down the pipeline, right? And it's also whoops. Try again. And it's also interesting to see this from the viewpoint of a video. So here, you see the reconstruction, which is being done frame by frame. And now, you see that there is a lot of jitter here. This is actually on purpose, because individual frames have been reconstructed starting from different random seeds. So they're going to, even though the input frames change only a little, the variance that you get here gives you a sense of how much geometric information is thrown away by a given layer in the architecture. So just to clarify here, that means that this is not changing a lot, but this is actually shaking all over the place. It means that this convolution feature here, they're essentially insensitive to this level of jittering, all right? And this is really quite interesting. But what I think is really remarkable, and that was completely unexpected when we ran this experiment, is that if you take the neurons there, which again, they're supposed to be, and let me show this again, they're supposed to be just class labels. So this should say, for example, there is a person here, although ImageNet doesn't have a label for person specifically. Well, anyway, so this should be completely abstract labels. It should not be possible to recover any specific image information from there. Even though that should be the case, you actually notice here that when you do the reconstruction, there is something which resembles a little bit the banner, you see? Now, this doesn't make any sense in principle, because this information should not be here. This, again, should be just class labels. Nevertheless, there is still a little bit of image-specific information even at this level of the architecture. So it's very odd, and it's not very clear what that's, well, I mean, maybe that's a limitation on the network, or maybe that's some useful property of the network, all right? So even at this very deep level, there is still some information which is image-specific. It's not completely abstract. Was this clear so far? Why I'm showing these images? Let's see whether this works. All right, so this is the same demo as yesterday. Oops, there you go. So start model again. Sorry, just keep switching resolution. It's not very good for demos, apparently. All right, let's try again. Okay. All right, good. So, all right. Okay, so do you know what a patas is? It's a monkey, apparently. So it's a particular type of monkey, and it is the monkey I've inverted here. So if you go deeper down, so these are the images that I constructed before, I think. You see that even this sort of scrambled mess is still being recognized as a, well, monkey, a patas monkey specifically. And these are the images I showed you yesterday. Black swan, well, I guess this was goose, yes. Cheeseburger, coffee mug, bullfrog, etc., vending machine, okay? Actually, no, I didn't show you this yesterday. I'm going to show you later. Anyway, so you'll see what some of these images in a couple of minutes, okay? So you have seen now that this reconstruction, actually, they really do, they are really classified by the network as the original object, okay? So, what this means is that really, so if you input those images to the network, well, for the viewpoint of the representation, they're equivalent to the ones that actually look nice to a human, but for a network, it doesn't really matter, at least if you cut the network deep down enough. So that's quite interesting, I think. Okay. Now, you can do many other things by playing with variants of this idea of visualizations. And specifically, I'm going to show you a couple of examples. So one is activation maximization. So now what we're going to do is we're going to take a specific neuron in AlexNet, for example, one class labels there, and then we're going to try to maximize the output of this layer, of this neuron, in fact, by finding an image which excites that a lot, right? So we pose that again as an optimization problem, but now the goal is not to reconstruct a reference representation phi naught, but rather to make the response to this neuron very large. So this is very dark, unfortunately, but, and I showed this image just a second ago. So do you know what so this is the image you get by reconstructing one of those neurons in AlexNet. Can you guess what this is? It's a black swan, okay? This is, I think, a goose, cheeseburger, coffee mug, frog, and vending machine. Okay. And remember that all these images have been generated starting from random noise. So you see here an example of this being run. So this is your starting point. You just want to maximize the last neuron, run through gradient descent, and this is what you get out. Okay. So this is the canonical black swan for the neural network, if you like. It doesn't look super realistic because the network, again, is not being trained to generate images. But this is what really excites that particular neuron. So you get an idea also the sort of invariances that are in there. And of course, you can play this game for any neuron anywhere in the architecture. So for example, I can visualize single neurons in conv3 if I want to. So this is what happens. So if you visualize neurons in conv1, but what you get back are these simple shapes, which in fact are just saturated versions of the filter you learn in conv1. Now the reason why this is all blurry is because there are those regularization terms, and all the neurons here have been reconstructed in one go for efficiency. So there is a bit of bleeding out. It doesn't really matter. So that's just because of the regularizer. What is important is sort of patterns you get here. Now you go to conv2, some sort of odd shapes start to appear. They're still relatively simple. And as you get deeper down, so you see 3 by 3 neurons being reconstructed, you see that each one of them is excited by very odd patterns. This is conv4, and you see here something that might look like a dog face, although it's pretty hard to say. How many of you think this is dog face? Yeah, quite a lot. Okay, probably this is dog face. Do you know why there is a specific neuron for dog faces in AlexNet? Yeah, about half on ImageNet is about dogs, actually. So that's maybe a limitation of the data set. Well, that's the ImageNet challenge data set, to be specific. All right, so deeper down, some more neurons. You see that very pretty pictures and very complex patterns start to appear, but to me, it's actually very hard to associate specific meanings to those things. Now, this may be a limitation of the way we are visualizing them, but I think the other reason is that we are looking at the individual neurons, whereas neurons probably make sense when you look at combination of them, and this technique doesn't do that. You could use it for visualizing combinations, but then you also need to find which combinations it makes sense to visualize. All right? Anyway, so this is what excites particular neurons in COM5, and then you can go deeper down. I guess these are the comparisons of the responses you get from different models, AlexNet, VGGM, VGG very deep, and they are sorted by increasing complexity. They are, the patterns are extracted from comparable level of depths, but that also would have to be defined properly. But you see that the complexity of the patterns that you reconstruct is actually increasing, all right, as you would expect. You can also play other games. For example, you can try what I call characterization. So what it means is that in this case, we're going to start from a given image x naught, and then we're going to try to make the response of the neurons that are already very active for x naught even more active. All right, so it's like if there was a neuron that would fire for a big nose, then this method here should actually make the nose even bigger. All right, so this is why it's called a characterization process. But of course, these neurons are not all that abstract, so when you apply this technique to, in this case, VGM, what you get is that if you get characterization out of COMP2, well, you tend to get essentially linear structure being emphasized out, all right? So this is the original image, and this is an image for which the COMP2 features which are strongly responding here fire even more strongly. Then COMP3, you see that you start to get curvilinear structures out. COMP4, you see that they're starting to close loops for some reasons. In COMP5, you start to see that the head of the fox is being emphasized, probably because COMP5 starts to be more semantic. And then if you do that from fully connected layer 6 to 8, what you get out are bits of the object being copied all over the place, and the most discriminated bits, which is apparently the fox head. So here again, you're losing information about the original layout, and this is what happens when you do categorization on that level. However, this is also interesting because this is a completely abstract pattern, which is not in the ImageNet training set. And even this one is somehow processed in a way which makes some sense, all right? So the salient features of these things are actually emphasized even more. And here you can see this thing in which the gong is actually replicated all over the place. And of course, you can use this also for art. So this is an example of COMP3 being emphasized on a video of Oxford. And so this original video playing, and this is what you get when you apply characterization to that. And you know, it looks pretty. Is that useful? Well, I'm sure it's useful for Adobe. It's probably not so useful for a computer vision scientist as such, but nevertheless, it's good stuff to know about. And in fact, it's good stuff to know about to an extent that I'm actually pretty excited about it. So I want to have a little interlude here and talk about it, about applications of neural network to art a bit more. So there are many ways of doing that, but one which is really nice is this idea of style transfer. So you can take an image of a painting and apply the style of that image onto some other target image that you have, for example, a picture that you took. How many of you are familiar with this idea of style transfer? Okay, not so many actually. I thought this was very popular by now. But anyways, how do you do that? Well, this is also interesting because, again, it teaches you a little bit of the sort of statistics that these different layers actually learn. So here what we're going to do is to take two images, X style and X content, right? So the style image will be an image from which we want to recover the style, say a Van Gogh painting. X content could be an image of your dog, say. So now we want to get a Van Gogh version of your dog. So the way we do that is by finding a third image X, such a way that when we compute these features, and this is a representation of, say, VG very deep, so as a pre-trained network for discrimination, well, what we're going to do is to try to match the statistics that the network computes, the representations that the network computes from this image to the representation of the style image and the content image, all right? So what we're going to try to do is to find an image X which somehow matches the representation of the style and the representation of the content at the same time. So it should be a sort of a mixture of the two. But crucially, we change slightly the statistics that we compare. So here, for the content, we do exactly what I showed you. So you just invert the representation as is in L2 norm. So that's exactly what I showed you before in terms of inversion. But for style, you do something slightly different. Instead of just trying to copy the features from here to there, you will try to copy only some statistics of them. For example, the correlation between different features in these channels. And here, you do that from a layer deep down because you want these comparisons to be abstract. Whereas here you do that from, for all the layers, including the shallow ones, because you want to copy the style of this image. So you want to copy, for example, the colors, which are much better represented here than up there. Okay? So that's the basic idea. You write this down as a optimization problem, and then you optimize X. This is a bit slow. There are ways of accelerating that, and we have one way of doing it, which we proposed recently in SML, which is a feed-forward network that basically replaces this optimization block. It doesn't really matter. It gets you essentially the same results. But here are some examples. So you must be familiar with this place. Okay? So now this is the image I'm taking the style from. This is being computed by an application which is called Vinci. There is another one which is called Prism, I guess, which is probably more famous because it came up earlier. This is our version, which uses a faster and probably slightly better feed-forward network for style transfer. So this is what you get if you transfer the style from this image to that. But now you can play this game and keep changing this, and you're going to get very pretty pixels out. Okay? So this is, well, I don't know the name of this painter anymore, but maybe you can tell me. All right, so you get that. From here to there, again, again. Yeah, this is probably very appropriate. From Jesus to, well, fishing. Again, this is actually pretty nice. So this is a pencil drawing, so it looks like it's been drawn with a pencil, blah, 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 and it can go on forever, essentially. Okay? So it looks very nice. Now, yeah, that's all. So this is interesting because it shows several remarkable properties, what kind of statistics is captured by these convolutional layers. But also, the network that we are using for computing these statistics, they have been trained discriminatively. All right, this was VGG very deep, which was very deep, which was trained on an ImageNet task for discriminating 1,000 different object categories. Nevertheless, these earlier layers learn things which are actually very useful for the purpose of image generation. Okay, so this is established a link between discrimination, or well, another link between discrimination and generation, which I think is very interesting. Okay, it's not on purpose; it just happens. But you know, there's another interesting properties of deep nets. Okay, so this is everything I wanted to say about this first part on visualization through optimization. Now I want to talk about backpropagation again, because I think there is some more interesting things to say about that. And I have time till 11. Okay. All right, so the time is good, so there is enough to cover everything, I think. All right, so what is backpropagation? Well, you should know already perfectly well what it is, because of Raquel's talk yesterday. But anyways, it's a process for which you take a deep network which ends in a loss term. So in this case, this number is should be small, provided that the network tells us that this is a bicycle, and it should be large instead if the network is wrong and tells this is a dog. All right. So at the end of the day, what I get is a function of the image and the label, which outputs a scalar. So the output lives in the reals, and what I want, and this function is parameterized in all the filters you have. And now, what you want to do for the goal of casting the descent optimization is to compute the gradient of this error here, this scalar, with respect to all the parameters, right? So backpropagation is a procedure that allows us to compute the derivative of the error, if you like, with respect to all these numbers, okay? Now, Raquel yesterday said that this is just a chain rule, and this is true, but from my viewpoint, there is one more ingredient which I think is actually very important. I mean, that comment is perfectly valid, in fact. So if you have, suppose we have a scalar version of the network. So all the variables here are scalars, and f1 to fn denote layers. It doesn't really matter, just functions. I'm going to reverse that. Why? Because now I want to write this as a formula. So you know, when you apply a function to an argument, you usually go from right to left instead of from left to right. So it's a bit unnatural when you draw it in a diagram, but it's very natural when you draw that as a, well, when you write that as a function. Now you apply the chain rule, so you want to compute the derivative of x of n, which say, for example, with respect to the input. So what do? Well, you take the derivative of the individual terms here, and you multiply them together, right? This is what Raquel was showing yesterday. And this is fine, and this is a good way of talking about backpropagation. However, there is a little catch. What's the catch? Well, these functions here are not all that simple. So they are functions which take a tensor as input, take a tensor as output, and they depend on parameters which are also tensors, maybe even more than one in the case of a filter bank. All right? So an input has a height, a width, a number of channels. The same is true for the filters. They have a filter height, filter width, number of channels, number of filters in the bank. And from those numbers here, you can compute how large the output tensor is going to be. In general, it's going to be about the same size as x. And then the number of channels here is equal to the number of filters you have in the bank. All right? So this is just convolution. Now, we're going to use again that trick of vectorizing arguments because this makes the math a lot simpler. So what we're going to do is to take x and vectorize it by interpreting these tensors as just a big vector, just stacking the values. We do the same for y. And vec of x is essentially the same function, but now this operates on the vectorized version of the tensors. So just notation, if you like. All right? So this is just your layer. You can always write it down like that if you want to. And now let's see. Let's try to compute the derivative of this guy. And this is where the problem is. All right? So we do that. So the derivative of, so what we want is the derivative of y with respect to x. But these are big vectors. So what we need to do is to take the derivative of each element in the output vector here with respect to each element in the input. Okay, so we can write that down as a matrix. So we put the vec of x as a row here, vec of y as a column, and then our derivative is essentially a matrix, and the value here would be the derivative of this particular element in the output with this particular element in the input. Right, can you see the problem? No? Okay, so we'll see the problem in a second. So if you do that, you can, in a network in which all these numbers are, all these guys are tensors, then this is what you get. You get matrix multiplications, and then eventually you get the matrix you want, which is the derivative of the whole function with respect to the input. Okay, again, back propagation. What's the problem here? Well, let's try to compute the size of this guy, all right? So if this is a tensor which is 32 by 32 by 512, this is typical, say, in VGG very deep. So 32 height, 32 width, and 512 feature channels. And suppose that y happens to have the same dimensions, then this guy here, just one derivative is a terabyte of memory. Okay, that's the problem. Right? So you really do not want to compute this. It's just impossible. And this is for one layer, right here, and then you have 150 in ResNet. Yeah, this is a problem. So you cannot pre-compute these matrices and then multiply them together in a trivial way. And I think this is where the smartness of backpropagation is, and maybe the reason why it's not just called the chain rule, all right? So backpropagation gives you a solution to that problem. So how does it work? Well, the first thing that you have to notice is that the last element in your architecture is going to be a real. Why? Because what we are trying to optimize is a loss, right? So what we're trying to optimize is just a real number. So at the very last level, y is just a scalar, all right? So vec of x is going to be something big, but your output is going to be something very small. So when you then draw this into this diagram, what you see is that now this matrix is not all that terrible anymore because, yes, x is big, but y is really tiny, all right? So if you compute how much space this takes, it turns out to take only 2 megabytes of space for the last level of AlexNet, I think, or something like that. No, sorry, not for the last level of AlexNet, for if your input tensor had the same dimensions as before, okay? So this one you can store, but that's only valid for the last level in the architecture, all right? So what do you do? Well, what you have to do is to notice that, okay, so the derivative of this guy we can compute because he has this particular shape, and the reason is that the last guy here is a real. Now we look at the last two guys together, and we notice that, yes, this is big, but all we want at the end of the day is the result of the product between this guy and that guy, all right? So if you think about it, multiplying this vector by this big matrix will give you another small vector, okay? And this one you can actually store. You cannot store this guy, but you can store this guy. And then you continue doing that, okay? Is this clear? Every time, you're only going to output a small vector, which is obtained by multiplying a big matrix by the small vector you got before, okay? Now, you might wonder, how can you do that? Because at the end of the day, to compute this multiplication, it seems you have to compute this matrix anyway, and I said this is intractable in most cases. Well, the trick is that all neural network toolboxes that you use, when they perform backpropagation, they have a functionality implemented in each layer that allows to compute this product without actually computing explicitly this big matrix. And that's the trick. So each layer can compute this product efficiently, and then you can chain up all these layers together because every time you're going to pass a small vector to the next guy. Okay, and this, of course, now is going backward. This is why it's called backpropagation, right? Because you backpropagate small stuff. This is what makes it computable. And in fact, you can do more. You can interpret that as a layer in your architecture. So this is a bit of a complex slide, I guess, but I'm going to try to do my best to explain it. So here what we have is f, which is one layer in your network. X is the input and y is the output, and these are big tensors. Now what we want to do is to define the backpropagation version of this layer. This is going to be a new layer, if you like, that goes the other way around. Okay? And so what's the meaning of this layer? So what this layer does is it takes the derivative of f of x with respect to x, okay? But crucially, f of x is now projected onto some vector p here, okay? So what is this p? Well, this will be the linearization of whatever happens after that point in the network, okay? But if you look at this from the viewpoint of a single layer, you have to imagine that you're taking f, multiplying with the inner product, the output of that by some vector or tensor p, and then you take the derivative of this guy with respect to the input. And crucially, the reason why you're doing that is because this guy here, how many dimensions does it have? The inner product between p and f of x. How many dimensions? 1, okay? This is the inner product, so it goes from 2 vectors, 2 tensors, to 1 number, okay? So you can do that, and the result of this is a vector. What's the dimensionality of this guy? Let's see whether we understand what's going on here. What's the dimensionality of this derivative? Dimensions of x. The dimension of x, exactly. So this guy here has the same number of elements as x. So if x is something you can compute on the way forward, then it means that this guy you can compute on the way backward. It's not going to take more space. Okay, so backpropagation in general takes twice as much space as the forward pass, if you like. And in fact, you can optimize it even further. All right, so this is a way of defining from f a new kind of layer that goes in the other way. There are several interesting properties. For instance, this goes backward by taking p, which is going to be the derivative you get from the layer above, and going down this direction. F of bp happens to be linear in p just because of the definition, right? So the backward network is linear in this chain. It's not linear in this argument, though. So here's how it looks in a neural network toolbox. This is our matconv.net, but other toolboxes would be similar. So you have a function in MATLAB, VLN and conv, that takes x, your tensor, the filters w and b. B will be the bias, and gives your output. Now we append to that the rest of the network. So this is a dashed because it could be anything. It doesn't really matter. So, but you have to imagine that this is there, and eventually this tensor is mapped to a real, which is your loss function. Now what we're going to do is to linearize the rest of the network by replacing that, which is a linear function, with just the derivative of that with respect to the argument y. So now it's a linear function. And now what we do is in the backprop mode, we call the same function, but now we pass to it not only x, w, and b, but we also pass this vector here, dz over dy, which is the derivative of whatever happens next. And what this does in backward mode, it gives us the derivative of dz again with respect to this argument here. From here you go to here. And also with respect to the parameters. And this is how backpropagation works, okay? And this, again, so this is something which is implemented automatically in these neural network toolboxes. And a lot of bright minds in, well, research as well in companies have thought how to optimize this to death, particularly on GPUs. But now we get also something quite interesting theoretically, because now we get a way of writing our forward network like this, and then we get a new network, which is what I call, or what we could call the backpropagation network, which goes the other way around, where all these layers are defined automatically from backpropagation. So this shows that with a bit of flexibility, you can think of these networks as computational graphs. And then once you have that optics, then you can actually do very interesting things with it. For example, interpreting backpropagation as a second bit of the network that you attach to the first one. Okay? Flip this over again, so we get a forward pass and the backward pass. All right, so that was, I think, interesting per se, but why have I spent 10 minutes explaining it? Well, because now we're going to use it, all right? We're going to use it again for visualization. So we have a forward pass, and then, for example, com, relu, max pooling. This would be a bit of AlexNet. And then by using this back propagation construction, we get the reverse direction as well. So we have max pooling back propagation, relu back propagation, convolution back propagation. And each one of these layers will take the derivative from the previous guy, but also, and crucially, the argument that the forward guy has. So this guy depends not only on dx1, but also depends on x0, okay, like this. Now, it turns out that depending on the layer, the amount of information you need to transfer from the top part to the bottom part actually changes. So if you think about it, convolution is linear, so the backpropagation direction does not actually depend on that, if you do the math. So there is no information to transfer here. For the ReLU, that's not the case, but instead of transferring x1, all you need to transfer is a mask that tells you which element of x1 were actually positive and which elements were actually negative. So we call this the on-off or sign mask, okay? And again, for max pooling, you don't need to transfer the whole of x2. You only need to transfer for each output neighborhood, which were the element of x2 that was actually pooled. So those we call pooling switches. Tell us locally which one were the maximum, okay? So we get a sort of reduced version of the architecture in which we transfer only the minimal amount of information to implement the backpropagation. And we like to call this bottleneck information, if you like, or sufficient statistics. Okay? Okay, why is this interesting? Well, because now, again, you can use this to do interesting things in terms of visualization. So the first one is what I call SaliNet here, which is an odd name, I admit. This is equivalent to a paper that we published a couple of years ago about network saliency. So this is essentially an idea to try to emphasize in an image which is the portion or the subset of the pixels that actually are relevant for the result that the architecture is actually computing. And all you do is a sort of saliency analysis by computing the derivative of the output, which will be your class label, with respect to all the pixels in the input. So that's just a derivative that you can compute with backpropagation, or you can see that as being the output of this backward network. And now you can do something very interesting. You can take this, okay, and you just do one change. So you get this ReLU backpropagation, which has this dependency, which are the on-off mask, and you remove that, and you replace that with standard ReLU, okay? Now that doesn't make any sense in a way. It's arbitrary. But if you do it, you get this paper, which is very famous, DConvNet, that I guess won the best paper in ECCV a couple of years ago, which is also a technique for visualization, all right? And, you know, DConvNet is great, but it's a bit heuristic because it's very hard to explain why they have done that. So this is explained as backpropagation. This one almost, but that bit is different for some reason. Now you can play games, and so we did that, and we created this thing which is called DSaliNet, which is a combination of these two ideas. So now what we're going to do is also arbitrary. We're going to combine this guy with ReLU, so we're going to take these two together. Okay, this seems a bit crazy, but why would we do that? Well, of course, because then the results that you get are actually pretty interesting. So if you apply DConvNet on AlexNet directly on those images, and here we're trying to invert a neuron in COM5, I believe, this is sort of the results you get. If you do DSaliNet, this is what you get. Here it's a bit hard to see, but you're going to see that what is being emphasized here are the people, all right? So usually this is showing black and white, and by taking the absolute values of the images so it's more clear, here I'm doing that for uniformity with the other visualizations. And if you use this DSaliNet, which combines this idea of ReLU backward and combined with ReLU backprop, you get something which is a lot crispier for some reason. And I think we actually know the reason for that. And this is a fully connected layer number 8 in VGG very deep, and so the difference is even more dramatic. So the DConvNet, you can sort of see the shapes of the objects, but not very well. If you do in SaliNet, this saliency map, you see these things being emphasized, but you lack a lot of structure. When you combine these two, you get both saliency as well as structure back for some reason. Okay? Now, oops. Sorry. All right, so there is so if you are interested in interpretation of what is happening, well, I'd like to refer you to the paper, so I would like to move to something else. But I would like also to, well, tell you something which is a bit of a negative result, actually. So when people proposed deconvolutions, the idea was that those would be useful for visualizing the behavior of different neurons. So the idea was that you would take a feed-forward network, select a neuron you wanted to visualize, and start this deconvolution process from that level. So the idea is you should see in the input image, so this process should highlight in the input image whatever is important for that neuron. So if you do that for this particular architecture and this house image, with two different neurons in pool 5 and fully connected layer number 8, this is what you get with the different methods. Actually, so this is a deconvnet, this is desalinet, and this is salinet. All right? Now, crucially here, what we're doing is visualizing different neurons. So this is the neuron which is maximally activated by this original image in pool 5. This is a random neuron, and this is inverting all the neurons activated at different levels with random noise. So what do you notice here? So here we're trying to visualize the maximal neuron. Here is a random neuron, and these are all the neurons together. You get the same stuff out. Okay. So deconvnet and desalinet and all these methods, they're not very good at visualizing different neurons. The stuff I showed you before, that's very selective for a neuron. This one isn't. Okay. So this one will visualize whatever is in the input image and is in general salient for the network. But by visualizing different neurons, you will not, one, be able to change the result, which means that there is no information about which specific neuron is being activated, only in general what's salient in the image. Okay, so when you use deconvnets, keep that in mind. That's a limitation. All right, so how are we doing with time? Yes, 15 minutes. Any questions so far, by the way? Nope, all right. And now I'm going to move to the most abstract part, which is the one I like the most, actually. But, what? Oh, there is a question.
Yeah, can you just talk a little bit more about why it's interesting to know what is happening in each neuron? Like, why is it, instead of trying to understand what about the image is generally important, why is it important to try to understand?
Because, so the question is, why is it important to understand what these deep networks are actually doing and what the different neurons actually mean? Well, the reason is that so there is what I would think is the machine learning perspective, maybe the DeepMinds and Facebook perspective, which is to say, we're going to create a general purpose learning machine that solves all the problems in the world, and then we don't care. Okay? Then there is, all right, but we are scientist perspective, so we want to know why things work. Okay? So the reason why we're doing all these things is because the network gives us some interesting properties and good results, but we don't understand exactly why. So we try to figure out how this is actually achieved. And that's one reason. The second reason, which is possibly even more important, is that if you understand what the network is actually doing, and you maybe can even build a theory of what the network should be doing, then once you have a theoretical understanding, it's guaranteed that you're going to be able to design better networks, better models, and in general be more satisfied with your life. Okay? So theoretical understanding is important, and all these are empirical evaluations and explorations, the purpose of which is to hint possible reasons why these models work, and eventually allow us to actually build a theory of deep networks. This is why they're important. For specific models, they can also have a diagnostic value. So you can use this to understand what the network is doing, what is failing, what is succeeding, which elements of the image are actually salient for a decision, and all those things. So there are many other reasons why this is interesting, but to me, the main thing is that this is a way towards a theoretical understanding of deep networks. And once we have that, if we ever will, then we can do great things, I think. All right, so last part, last 10 minutes. Right, so this is interesting because, again, it looks at the problem of representations from an abstract, a slightly more abstract perspective, but it's also very intuitive and very practical. So suppose we train a network from 2 different data sets, or perhaps even the same network, but starting from 2 random seeds. So remember that your optimization procedure, which is stochastic linear descent, as we have said many times in the school, well, it's just going to find the local optimum, and it's actually not a very sophisticated optimization algorithm, so there is no reason to expect that it would find consistently the same point. In fact, it won't. Okay? So now suppose we have learned CNN A, which goes from an image to some vector representation. This could be given level of AlexNet, could be just be the end, all right? Now suppose we repeat the process and we train CNN B. This is again AlexNet. I just started from a different random seed and I'm training on the same data. So what do you expect? Do I get the same network twice or do I get something different? Based on what I just said. In general, because you're optimizing the networks using stochastic linear descent, CNN A won't be the same as CNN B. Surprisingly, however, no matter how many times you try, your performance tends to be exactly the same. So the networks themselves, if you look at the parameters, they're completely different. But the performance of the networks, no matter how many times you run SGD from scratch, is going to be pretty much identical, which is very surprising. Okay? So the question is, are these two models really different or not? So what we're going to do is to try to find out by learning a mapping which goes from this representation to that representation. And so the idea is that we can compute phi of A of x, then apply this mapping, and we should be able to get back phi of V of x. And of course, this mapping has got to be very simple, otherwise this might do too much work, and we want this to be a simple equivalence relation. So we're going to make the assumption this is actually a linear map. So it can only change the features in a simple way. All right, let's see whether we are successful doing that. So how do we do that? So our question is CNN A equivalent to CNN B or not? So what we're going to do is to cut CNN A at some level of depth, for example, conv4. We do the same with phi of B, and we ask whether these two subparts of the networks are the same. So we do that. So we take the first bit from a network, the second bit for the other, and then we glue this together by applying this transformation we learned. Okay? Who is this? I know. This is too difficult. So this is Dr. Frankenstein. Okay? So this is what we call a Franken network because it has a bit of a network and a bit of another, and there is some stitching in between. Okay? So what we want to know is whether the monster is alive, essentially, provided that we do the stitching well enough. So what we're going to do is we're going to freeze these layers. So these are pre-trained from two different random seeds, and then we learn only this guy, again, on the ImageNet task through SGD. All right? Now, of course, we can play this game at different level of depth. So we can take conv1 from one network and the rest from the second. We can take conv1 and conv2 from one network and the rest from the second. And we can apply the stitching at different levels of depth. Okay? So now we're going to see what sort of performance we get when the stitch moves from shallow layers to deep layers. So first of all, the baseline performance is here. So this is about 24% top 5 classification error for AlexNet on ImageNet. This is rather typical. Actually, in fact, I think this is about 20%. Okay? Then what we're going to do is to take network AlexNet A and AlexNet B, stitch them together without doing anything here. We just feed the output data directly onto the input of this network. And you see that now your error is 100%. So you go from 20% error to 100% error. Now, this is really bad, but it's expected because the parameters of these two models are completely different, and there is no reason why feature number 1 here should correspond to feature number 1 in the second network. That's arbitrary. So what we do is we learn this layer that fixes this, if we want, ordering issues, and then the performance is essentially restored. Doesn't matter what we cut. All right? So what this means is that up to a simple linear remapping of the features you have learned in the first case are essentially the same as the feature you have learned in the second case. Is this clear? So it means that no matter how many times you train a network, essentially you get the same features, just under a slightly different parameterization that you can recover through learning, essentially. Now, as you see, the equivalence is nearly perfect for conv1, and the reason is that conv1 features are very genetic. Slightly worse for conv5, that becomes a bit more specialized to problem, but also probably a bit more sensitive to the initial points when you do SGD. However, the reconstruction is still very, very good. So you lose maybe 1 or 2% points, but the equivalence is really there. Okay? And there is a really big jump here. Now, we can play this game even harder. So what we're going to do now, which is more interesting possibly, is we're going to train a network on ImageNet, and then we train a second network on a different data set. So now what we want to see is whether we're learning the same sort of stuff from two different data sets or not. So ImageNet contains objects, and the other data set we're going to use here is a places data set, which I believe is Antonio Torralba, right? Okay. which contains instead scenes. So the content of these two data sets is actually fairly different. So we learn first network here, second network there, and then we look at this Frankenstein monster and we see what happens. Well, again, if you don't learn any stitching, performance is dreadful. This is the baseline performance. And you see that as we stitch deeper, deeper and down, then initially the reconstruction of the features are basically perfect. As you go deeper down, it gets worse and worse. Now, this is because the very low-level features, as you might expect, they're very generic. So it doesn't matter whether you train them from bathrooms or dogs, you're going to learn the same COM1 filters. COM2 is about the same, COM3 is about the same, but then in COM4 to COM5, things start to be a little bit more specialized. So you cannot get perfect equivalence between the two models anymore. Okay? And then last set of slides with the most interesting concept possibly. So try to stay awake. So this was about network equivalences, but so we learned two models. We want to understand whether we learn the same things or different things. Now what we want to do is instead take a single model and ask ourselves what are these features actually doing. And so before I do that, I would like to go back to this idea of representation and similarity between data based on representation. So what's the goal of representation? So if you're an old school computer vision person, then what we used to think is that a representation is good if you can map some sort of semantic similarity in the image space to some vector similarity, so vector distance. So that's the typical slide that you might have seen a couple of years ago in Vision. So you get 3 images, and then 2 of them are congruous in the sense that they contain 2 bicycles, and the third one contains a dog, so something else. Now what you want is that your mapping takes this into some vector space where these 2 guys are close because, well, they are 2 bicycles, and these 2 guys are far away because one is a bicycle and one is a dog. At the same time, you want these 2 points to be the same, regardless of the fact that these are actually 2 different types of bicycles, or maybe the viewpoint is different. So what you want to do is a trade-off between invariance to irrelevant factors like viewpoints or illumination, and then be instead very distinctive with respect to changes in the semantic content of the image. So you want dogs still to be far away. All right, so in principle, you could say, all right, I want my representation to do that for me. Why? Because if you have this property, then in this space, it should be really easy to tell bicycles apart from dogs. Do you think this is a good way of thinking about representation? Can you see any flow here? It's not an easy question, so if you don't see it, it's okay. All right. So this is the reason why this is, I don't think, a very good way of looking at the problem. So suppose that you're asking whether these 2 are the same category. Well, of course they are. There are 2 cars. Assuming that your category is cars. So these 2 vectors should be close. Suppose now you ask yourself whether these are the same colors. Well, now these 2 vectors should be far apart. Okay? So what this means is that this notion that we're using in computer vision for a while, or well, I should say, the way we're explaining some things in computer vision for a while, was a bit flawed in the sense that it was task-specific. So representations are much better understood when you look at multiple problems, I believe. And therefore, this idea of invariance and distinctiveness is not enough. All right? So you cannot just be invariant to something because the thing you're invariant to, which is color in this case, might actually be relevant for another problem you might want to solve. So what's the right question to ask? Well, I don't have a very good answer, or an absolute answer to that. But I think one good question is equivalence instead. So what you want to know is, when we change the image, how is our representation reflecting that change? And we call this equivalence. It means we change something in the image, and we expect the representation to change in some predictable and hopefully simple way. All right, so here's how this works. We have an image X. We look at representation in feature space, phi of X. Then we take a transformation G of the image. So, for example, we flip this left to right, and we look at the representation of the flipped image, which is somewhere here. And now what we want to see is whether there is a corresponding transformation in feature space. So from G here, which is just flipping the image left to right, we want to see how this maps into feature space and want to know what this means to flip something in the representation space instead. And of course, the point is that this has to work for any image we find. So we freeze the transformation we apply here, and we want this to work for any possible image, right? So what we want to do, whoops. Yeah, is to satisfy this equation. So we want to find a map mg, which is the equivariant map, such that we can move the transformation g applied to the image out of the representation. Okay? Now, what can happen is that this map exists and is easy to find. Sometimes this map can also be the identity. That means that there is no difference in the representation of left car and right car. Maybe it's something maybe something useful, maybe something that's not useful. Sometimes the mapping does not exist, or if it exists, it's just intractable. All right. So basically, we have three cases. Yeah, there is a simple mapping. The mapping could be the identity, or there is no hope of finding a simple mapping that satisfies this equation. So how do we do that in practice? So again, this is about probing an existing architecture. So I think Max is going to show you how you can actually use this to learn architecture to have that property, I think. No? Sorry, it won't. But anyway, so this is about probing properties of an existing architecture. So we'll train this on ImageNet. We don't worry about transformation when we do that. And then we ask whether this equivariance transformation has been found out automatically or not. So we take an image, transform pair there, we compute the mapping, and then we ask ourselves whether we can find an MG that does that. Okay? We assume that MG has a particularly simple form. It's going to be just a linear mapping, as before, plus some permutation of the features, which essentially track the geometric motion that is there in the input image. All right? So, and then you see this applied for hog. Let's see also how I'm doing with time. Not much. And let me just switch to the results slide here. So blah, blah, blah. You can do it for this network in various ways. So now what I'm going to do is do exactly that. So I'm going to take an image X, which is a upright goat, I believe. Then I'm going to flip it upside down. This is the, again, baseline performance of the network, 20%, as before. If I do the flipping, you see that the performance now is really bad. So it goes from 20% to about 50, 55% or plus. Now, what I'm going to try to do is to, and let me skip that. What I'm trying to do is to essentially compensate for this flipping by learning a layer in between the network that actually does the reverse. All right? So I compute from the flipped image, COM1, COM2, COM3, and then I learn a very simple transformation that tries to undo the effect of flipping, and then I continue doing what I was doing before without any change. So now if this is successful, if learning this flipped map in the middle of the architecture actually works, well, that means that I can essentially reproduce the effect of flipping in the feature space directly. If I'm not successful, then it means that it's not possible to get this equivariance for this particular network at a particular level. So if you see what happens, you get this so equivariance works very well for the earlier layer, COM1, COM2, COM3. But again, it starts to drop away when you look at COM4, COM5. So what does it mean? What's the take-home message here? It means that this level here, they really act as sort of genetic codes. And when you transform the image, there is a simple, this is reflected by a simple transformation of the representations at this level. But when you start flipping your image and look at what happens in COM4 and COM5, probably because those are already a little bit more semantic, then you cannot undo this effect of flipping anymore because those are computing things which only make sense, for example, if you look at them upside in with the correct orientation. Okay? And you can play this with many transformations. All right, so I think I already had my summary slide before. So why are we doing all this? Again, because we want to understand deep networks, and one way is visualization, but the other way is actually trying to probe systematically statistical properties that these models actually have, all right? And so by combining these and possibly other techniques, we hope to be able to actually gain some sort of intuition of what this model do. Once we have that, maybe also develop some sort of theory. Thank you. Questions?